Good morning. This is P. Venkata Mahesh, Assistant Professor in Mechanical Engineering Department, Institute of Aeronautical Engineering. We were discussing one subject which is called Applied Thermodynamics, which is for 4th semester Mechanical Engineering students. And in that, we were discussing one topic on one module related to refrigeration. And in that refrigeration module, we have seen what is a Carnot cycle, what is a vapor compression cycle, and we have done some problems on Carnot cycle, reversed Carnot cycle actually, and we have also seen what is how the ideal vapor compression refrigeration cycle and how it the actual deviates from the ideal vapor compression refrigeration cycle. And we also have seen some problems solving analysis of vapor compression refrigeration cycle, and as well as some problems also we have seen. And in this class, this particular discussion today, we will discuss about the air refrigeration cycles and in particular about the reversed Brayton cycle. Now, if you remember the Carnot cycle discussion, this is the diagram that we have used there. So in this diagram, this heat exchanger is there, and this is another heat exchanger. This is a low temperature heat exchanger. This is a high temperature heat exchanger, and here a turbine is there, and here a compressor is there. So here now the same setup is can be valid for the reversed Brayton cycle also. But then you can say what is the difference between the reversed Carnot cycle and reversed Brayton cycle. Now coming to reversed Carnot cycle, this is the diagram. The top one is for reversed Carnot cycle. This is for reversed Carnot cycle, and this is for reversed Brayton cycle. Now, what is the basic difference between these two? So this diagram, if you see, here there is a compressor, there is and a turbine which are connected, and there are two heat exchangers which are working at different temperatures. Say suppose if these heat exchangers are working at some constant temperature, then it is called the reversed Carnot cycle. And if these heat exchangers, if they are running or working at some constant pressure, okay, then this particular diagram is for reversed Brayton cycle. So that is the only difference. But in practice, if you see, to maintain a constant temperature while heat is being rejected, or to maintain a constant temperature while heat is getting absorbed into the system is not practical. Okay, it is not practical. But you can try for a constant pressure heat addition or a constant pressure heat rejection. Okay, so this is a constant pressure heat rejection, and this is constant pressure heat absorption. So this is the basic difference between the reversed Carnot cycle and the reversed Brayton cycle. We will see what is there in these cycles. If you see similar terminology, if you want to give, this is 1, this is 2, this is 3, and this is 4. So this is a constant entropy process, and this is a constant entropy process, and this is a constant temperature process, and this is a constant temperature process. So here what is there? The pressure is increasing. Okay, the pressure is increasing from 3 to 4. So, and here from 1 to 2 the pressure is reducing. So here it is a constant entropy or isentropic compression process. So it is a isentropic compression process wherein we are supplying some work. Okay, it is a isentropic compression process where we are supplying some work. And coming to this process, it is an isentropic expansion process, and here we are gaining some work. Okay, this process is developing some work. Here the process between 3 to 4 is consuming some work, and here the process between 1 to 2 it is giving some work. Say suppose the numbering is little different here. This is from 1 to 2 expansion process. So I can take this as 1, 2, 3, 4. So the 1 to 2 is an expansion process. So the 1 to 2 is expansion process, and it is a constant entropy process or isentropic process. Ideally it is isentropic process, but actually because of certain reasons that we have already discussed in the topic of vapor compression cycle, it will be generally deviating from isentropic process and it will be a polytropic process. Now here from 2 to 3, from 1 to 2 it is expansion process. From 2 to 3, here this is called evaporate. Okay, and this is called the condenser. If there is a phase change, okay, if there is a phase change, then this is a evaporator and this is the condenser, as in the case of a vapor compression refrigeration cycle. But here in air standard cycles, there is no change in phase, because all along the cycle from 1 to 2, 2 to 3, 3 to 4, 4 to 1, the phase is only air. It is only gas. So there is no phase change. So what to do? What to call this? It is a low temperature heat absorption process, and it is a high temperature heat rejection process. So here what it is doing, it is taking heat from a low temperature reservoir, which is generally the space which is kept at lower temperatures are called the refrigerator. So this is the refrigerator, and this heat exchanger, it will absorb heat from the refrigerator and it will give the heat to the surroundings. So the high temperature heat exchanger, the reservoir is the surroundings, and the low temperature reservoir is our refrigerator or the space which is being cooled. Now, so what we were discussing, the point 1 to 2 is isentropic expansion process, and 2 to 3 is it is a heat absorption process. In case of Carnot cycle, it is a constant temperature process. You can see here a constant temperature is maintained. But in case of a reversal Brayton cycle, you can see a constant pressure is maintained. And from 3 to 4, it is isentropic compression process where it absorbs or where it takes some energy and it converts that energy into the pressure of the fluid inside of the working fluid. Now at 4 there will be the highest pressure. You can see here this is the highest pressure, and from 4 to 1 it is a constant temperature process in case of a reversal Carnot cycle, and it is a constant pressure process in case of a reversal Brayton cycle. So this is the basic difference between reversal Carnot cycle and a reversal Brayton cycle. So in order to make the reversal Carnot cycle a practical one, what they did, a small change they did, and that change is, instead of a constant temperature process, we are taking a constant pressure process. Now we will see the analysis of the reversal Brayton cycle. Now this diagram is the typical diagram which is shown in our Rajput, the thermal engineering Rajput, which we are being referred. Okay, and the previous one is this, that is the general diagram. So this is the diagram for reversal, specifically for reversal Brayton cycle. And here this is the refrigerator or low temperature heat absorption process, and this is the air cooler, where instead of directly giving this heat to the air from the heat exchanger, what we are doing, we are cooling this air which is being hot, which is hot in condition, by cooling water. So we are circulating some cooling water, and we are cooling the hot air which is coming out of the compressor. So the basic components are, this is the compressor, this is a heat exchanger, and this is expander, and this is the refrigerator. Now here if you remember, in case of vapor compression cycle, we have removed this expander or turbine, and we replaced it with an expansion device, expansion valve, which does not give us any work output. Why? That also we have discussed. After condensation, it is in a liquid form, and in liquid form there is no change in volume literally. So because of that, the work output will be very less, and since the density is very high, the size of the equipment also will be very high. So the expander is removed in VCR, the vapor compression refrigeration cycle, and it is replaced with an expansion valve. And now coming to this reverse Brayton cycle, since the air is the working fluid, the hot air can give us a reasonable work output. So we are using an expander or turbine for expansion process. So this is an expander, or sometimes it can be a turbine, and then it is the refrigerator which we are having our concentration on. So here the entire discussion is on refrigeration process and how that refrigeration effect is obtained with different cycles. So the first cycle is reversal Carnot cycle, which is an ideal cycle which is not practical. The second one is vapor compression cycle, and the third one is reversal Brayton cycle that we are discussing now. Now here, this is the typical schematic diagram of the reversal Brayton cycle that we can see in many of the textbooks. Now coming to the analysis of this reversal Brayton cycle, with the help of these diagrams, we will see how to analyze this reversal Brayton cycle. Say suppose M is the kg of air, mass of air that is being circulated. Okay, M dot, sometimes it can be M dot, mass of air. Say suppose it is a constant closed cycle. So if it is a closed cycle, the same air is getting circulated inside this cycle. So if it is an open cycle, what happens is here a fresh air will be taken and here again this fresh air will be rejected. So in that case, what we'll do, how much air is being circulated per unit time, that also we can take. Now here what we are doing, we are taking that m is the mass of air that is being circulated inside the refrigeration cycle. Now what is the heat absorbed? The heat absorbed is nothing but mcp delta T. Okay, heat absorbed is nothing but mcp delta T. So mcp delta T is the heat change in heat, or heat added or heat rejected from the system is given by mcp delta T. Now what is m? M is mass of air and cp is specific heat, constant pressure specific heat. Okay, specific heat at constant pressure. Now because we are using here constant pressure process, we are taking here constant pressure specific heat. And what is this delta T? So here there is heat rejection, means input temperature is very high and outlet temperature is low. Okay, input temperature is high and output temperature is low, then it is a heat rejection process. And if it is heat absorption process, the input temperature is or inlet temperature is low, the outlet temperature is high. So if the heat is being absorbed by the body, as a result of it, what happens is the temperature of the body increases. If the heat is rejected by the body, as a consequence, the temperature of the body goes down. So this is heat absorption process in the refrigerator, and this is the heat rejection process in the heat exchanger, or here it can be called as a cooler. Now the cooler doesn't mean that it is cooling the space. Here the cooler means it is cooling the air being circulated inside this cycle. Okay, so we should not get into that confusion why cooler is used. It is heat rejected in air cooler. It is an air cooler which is cooling the air inside this cycle. It is not giving us any cooling effect for the room which is under consideration. So this refrigeration process, what it is doing, it is cooling the space which is under focus. Now delta T in case of the heat absorption process is T3 minus T2. Since T3 is higher than T2, T3 is greater than T2, so the delta T is T3 minus T2. Now the delta T in case of the air cooler is T4, the inlet temperature, minus T3, the outlet temperature. So T4 minus T3, it is a T1. T4 minus T1 is the heat rejection, and T3 minus T2 is for heat absorption, that is the delta T. Now what is the work done process? So work done process is given by N by N minus 1 into the PV minus PV. PV at outlet minus PV at inlet. So what is this pressure? So this pressure and volume at the outlet of the compressor minus pressure and volume at the inlet of the compressor. So at the inlet of the compressor, the pressure will be very low. At the outlet of the compressor, the pressure will be very high. And the resultant work formula is n by n minus 1 into P4 V4 minus P1 P3 V3. So it is the inlet is will highlight the compression process. So this is the compression process. In this compression process, this is the inlet condition and this is the outlet condition. So the polytropic work, if we consider a polytropic process, which is the actual process, and for polytropic process, the work done is given by n by n minus 1 into P4 minus P4 V4 minus P3 V3. The inlet pressure, the outlet pressure and volume, and inlet pressure and volume. Now similarly, for the case of expander, so the expander is what it is doing, the pressure is reducing, the volume is increasing. The pressure is reducing very high, I mean very much. The reduction in pressure is very much as compared to the volume. So the product of pressure and volume at the inlet of the turbine, this is the inlet of the turbine and this is the outlet of the turbine. So at the inlet of the turbine, the pressure and volume, the product will be very high. At the outlet of the turbine, the pressure and volume will be very low. So the work done by the turbine is P1 V1 minus P2 V2 into n by n minus 1. So if I want the net work, what is the net work? Since this is compressor needs some work and the expander is supplying some work. But if the entire work required by the compressor is supplied by the turbine, then it is not possible. I mean, it is not possible for the turbine to supply the entire work required by the compressor, because these are at higher temperatures and these are at lower temperatures. Since that is the case, what is happening is we need to supply some extra work. What is the net work that is being supplied by us? That is equal to work taken by the compressor minus work given by the turbine or expansion device. Okay, the expander. Whatever the work that is given by the expander. The work taken by the compressor minus work given by the expander is the net work supplied to the cycle. Okay, so that is our main interest. Why we are doing all these things? We need to find COP, and COP is nothing but the amount of heat absorbed in the refrigerator divided by net work. So that we have to find. Now the net work is work taken by the compressor minus work given by the expander. And if I substitute the formula of the work, compressor work and the expander work, it is like this. So what is the previous one? You can see P4 V4 minus P3 V3. This is the compressor work minus P1 V1 minus P2 V2. This is the expander work. So if I simplify this, if I take the minus inside, this will be minus, and minus of minus, it will be plus. So this is the net work supplied by us to the cycle for getting the refrigeration effect. Okay. Now if it is an isentropic process, what we have to do? The N should be replaced by gamma. Okay. Now, further simplification, if you see, so this is what we ended at. Now, P1 V1 from the gas equation, universal gas equation, P1 V1 is equal to mRT1. P2 V2 is equal to mRT2. P3 V3 is equal to mRT3. P4 V4 is equal to mRT4. If I substitute the P1 V1, P2 V2, P3 V3, P4 V4 in terms of mRT values, this equation will become this equation. So P4 V4 is equal to mRT4, P3 V3 is equal to mRT3, P1 V1 is equal to mRT1, P2 V2 is equal to mRT2. Now, if I take the MR, because MR is constant for all the terms here, the inside value is equal to T4 minus T3 minus T1 plus T2. Okay, and now this, if I want to see the isentropic one, so the isentropic process is equal, I mean the polytropic process becomes isentropic process if the power, the process is PV power n equal to constant. So this is the characteristic equation, and in this characteristic equation, if this n is replaced with gamma, then it is giving us the isentropic process. Now R, the relationship between R and J is R is equal to Cp into gamma minus 1 by gamma into J. Okay, R is equal to Cp into gamma minus 1 by gamma into J. Now, this R by J, okay, we have this equation R is equal to Cp into gamma minus 1 gamma into J. Now, in this equation, if R by J is replaced here, what it will be? Cp into, Cp is there, into gamma minus 1 by gamma. So this is a polytropic process. For polytropic process, it is n by n minus 1 into gamma minus 1 by gamma into mCp into this equation. Now, if it is a isentropic process, then n is equal to gamma. So what happens? N and gamma will get cancelled, n minus 1 and gamma minus 1 will get cancelled. So the net work done for the isentropic process is equal to mCp into the temperature difference. So this is nothing but, so the temperatures, the T4 minus T1, this is heat rejected, and T3 minus T2. Okay, T3 minus T2, that is the heat absorbed in the refrigerator. So this minus this will give the network. So if the compressor and expander are working at isentropic process, then the network can be obtained by simply taking the difference of the heat absorbed and heat rejected. Okay. Now, so we have seen what is the network and what is the net heat or the heat refrigeration effect that is provided. Okay. Now, what is COP? COP is nothing but heat added or heat absorbed divided by the net work supplied to the compressor. The network means that here it should be Q. So the net work supplied by the to the compressor is, as I discussed in the previous slide here, it is a difference between heat rejected minus heat absorbed. So the same thing here shown. Okay. Now what is this? This is a heat added by net work done. Heat added by net work done gives the COP. Now, what is the heat added or the refrigeration effect? It is MCP into the change in temperature in the refrigerator. So, that is equal to T3 minus T2. So, MCP into T3 minus T2 is nothing but our heat added. And for polytropic process that we have discussed, the net work is equal to n by n minus 1 into gamma minus 1 by gamma into m into Cp into T4 minus T3 into T2 minus T1. This equation. Now, if I simplify this MCP, if I cancel out, what is the equation? This is equal to T3 minus T2 by this value. And if it is a isentropic process, then these two values also will disappear. Now, if I compare this with the Carnot cycle, this is the COP of a Carnot cycle. That turns out to be T2 by T1 minus T2. Now, what is the Carnot refrigeration cycle? If you remember, so this is the Brayton cycle. Now, similar to this, what is our Carnot cycle diagram? So the Carnot cycle diagram is, as I have discussed, it is these two are constant temperature process. And this is T2 and T1. That is what they are taking. Now, here the Carnot cycle COP is simply dependent on the temperature of the condenser or the heat rejector and the temperature of the heat absorbed. But in case of the Brayton cycle, it is dependent on the temperature at the inlet of the heat refrigerator, outlet of the heat refrigerator, inlet of the cooler, outlet of the cooler, all these things. So, the COP will decrease little bit as compared to the Carnot cycle COP. So the COP of the Brayton cycle is less than the COP of the Carnot cycle. Now coming to the advantages and disadvantages of the Carnot cycle, the air refrigeration system or the reversed Brayton cycle. So this is compared to the VCR, the vapor compression refrigeration cycle. If I compare the reversed Brayton cycle with the vapor compression refrigeration cycle, where we use the NH3 as ammonia as refrigerant. So in vapor compression refrigeration cycle, we use ammonia, and in air refrigeration cycle, we use air, and air is freely available everywhere, and it is not a flammable substance, and even if there is a leakage, there is no problem. Okay, only the efficiency will go down, but it will not affect the people around it. But if I use the vapor compression refrigeration cycle and we are using an ammonia as a refrigerant, what happens is if there is a leakage, there is a chance of the fire getting attracted, or even it is not good for the people surrounding. So it is cheaper. The reverse Brayton cycle is cheap because air is abundantly available everywhere, but ammonia is not available everywhere. As compared to other refrigeration systems, the weight of air refrigeration system per ton of refrigeration is quite low. Because of this reason, the system is employed in aircraft. So in aircrafts, if you see, the COP is not important. Okay, there the uh, the refrigerant is important. So the air is abundantly available in if aircraft goes in upper atmosphere also. What happens is we can use a open cycle reversal Brayton cycle, and we can take air from the atmosphere and reject air into the atmosphere. We can take cool air from the atmosphere and reject the hot air into the atmosphere. So that is the reason. And another reason is compared to the weight of the cycle, the refrigeration effect produced by the reverse Brayton cycle is more than the vapor compression refrigeration cycle. So because of this reason, we use the reverse Brayton cycles in aircrafts. So what are the disadvantages? So the COP is low. The COP is low for the air refrigeration cycles as compared to that of the vapor compression refrigeration cycle. And what is the weight of air required? So if I use a very less quantity of ammonia also, I can get more refrigeration effect. But for the same refrigeration effect, I need to supply much more volume of air as compared to the ammonia. So what is the reason? That it is the sensible heat. Here it is in the form of sensible heat. In a reversal Brayton cycle, there is no change of phase. As I stated in the beginning of this discussion, there is no change in phase. But in case of the vapor compression refrigeration cycle, there is a change of phase. So when there is a change of phase, you can use the latent heat. But in case of when there is no change of heat, we are restricted to the sensible heat exchange. Okay, we can use only the sensible heat of the fluid, which is used as a refrigerant. That is the reason we have to supply more air for the same refrigeration effect as compared to the ammonia in case of vapor compression refrigeration cycle. So this is about today's discussion. And in summary, what we have to discuss, what we have to remember. The first one is the reversal Carnot cycle and reversal Brayton cycle. What is the main difference? The heat addition and the heat rejection process, they are at constant temperature in reversal Carnot cycle and at constant pressure in case of reversal Brayton cycle. The second one we have to remember is in vapor compression refrigeration cycle, we are using the phase change, or we are using the latent heat of the liquids, and in case of reversal Brayton cycle, we are restricted to use only the sensible heat because there is no phase change. Because of that, the COP is the weight of air, the mass of air required is more than the mass of refrigerant required in the VCR for the same refrigeration effect. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.